It's a pleasure to introduce Dr. Joel Leja from Penn State. So Joel is the Dr. Keiko Mia Ross, early career endowed faculty chair, and then an assistant professor of astronomy and astrophysics. And before coming to Penn State, he was a postdoctoral fellow at Harvard Smithsonian. And before that, he received his PhD in astronomy at Yale University. Okay. So Joel does a lot of interesting stuff. Is that good?
Yeah. That's great. I'll tell you all about it.
Yeah. I can do a bit. So Joel was named is one of the highly cited researchers. Clarivate highly cited researcher in 2003, 2004, which means he's one of the top 1% of cited researchers in astrophysics. And his research aims to understand how galaxies form using large ground and space-based telescopes, large surveys, and fast computers. So he specializes in modeling observations of the galaxies and in data-intensive astrophysical methodologies. And today, Joel will be talking about rapid inference of galaxy properties already moving in the age of deep and large-scale surveys of the universe.
Cool. Awesome. Thank you, Anne, for the lovely introduction, and thanks everyone for coming here at 9 a.m. on a Sunday. So I spend most of my time thinking about how galaxies evolve. How did things like the Milky Way get here? And this is a field with a lot of problems, which is a good thing. But specifically, the universe is very hard to model. And this is largely due to scale problems. It's very hard to mix, on one hand, cosmology, spanning hundreds of megaparsecs, and on the other hand, quantum physics, on very small scales. And so there's a lot of kludges that have been introduced to try and marry these things two together so we can do this kind of modeling, but it just makes it intrinsically hard. And I'll tell you how that works in a second. But basically, I think we really need these high-dimensional, fast inference processes to really solve this problem. And that's why I'm here. I'm here looking for solutions to a lot of the challenges we have. And so I think next generation tools like simulation-based inference are kind of already completely changing the way we do observational astrophysics and cosmology. And our inference pipelines are going to look completely different in 5 years than they do now. No one's really prepared for this, not even people like me who are thinking about it all the time. Really, I mean, I was a postdoc just 5 or 6 years ago, and what took me millions of CPU hours on Harvard's computing clusters, now one of my students can do in a couple of days on a laptop using tools like SBI. So this is completely transformative, and the speed increases are actually maybe the most boring part. I think the exciting part is the new types of science questions we can ask when our models are fast, accurate, and very high precision. So that's what I'm going to talk about today. It's a bit of a different style. I'll have a lot more pictures and I'll say a lot more things, but I won't have very many equations. It's just not how my brain works. So, all right, let's get started. Okay. I'll be talking about the work of some of the folks in my research group, some of whom are here, actually. Emily Burnham, she was here. She actually left, but she had a poster right over here. It was great. I'll talk about her work. I'll talk a little bit about Dr. Bingjie Wang, who is actually the next talk, so I won't talk that much about what she's doing. She'll tell you herself. And also Dr. Ija Lee, one of my former grad students, and Elijah Matthews, one of my current grad students. So you'll see their faces all over the slides. This is the Hubble Deep Field. This is perhaps the most important astronomical picture of all time, arguably. There's a few up there. This is definitely one of them. This is the first time we pointed Hubble at a very, very deep field and just stared for a couple of days, and out of this image come all sorts of distant galaxies. Of course, all I see are problems. And how do we model these things? How do we learn from them? And one of the first things you want to know when you see a picture of the deep universe is, how distant are all of these things? Hey, that is one of the key problems in astronomy, measuring the distances to objects. So here, these are all just labeled with something called redshift, which I'll refer to often throughout the talk. This refers to distance or look-back time in the universe. Galaxies themselves, all of these things you see are galaxies, they are cosmic ecosystems. They have a ton of physics going on inside, and this is the source of my problems. So hidden inside of them are this sort of rich information about the astrophysics of the universe. Their formation histories are all kind of hidden inside of the stars, the production rate of heavy elements, things like carbon, nitrogen, oxygen, iron, all the things that we care about that eventually turn into things like you. Things like cosmic dust, the progenitors of exploding stars that tell us a lot about the universe. Things like cosmology, we use galaxies to trace those. The evolution of stars, fantastic laboratories. Okay, so these are, like I said, they are the cosmic ecosystems of the universe. All these things live together and interact with each other. And my job is to kind of try and figure out how that all works and see how these things form, how things like the Milky Way came to be. So to be more specific, I infer properties by fitting observational data with models. So we take these beautiful galaxy data. In this case, this is Andromeda, one of our biggest neighbors, from the radio all the way out into the X-ray. You see it looks very, very different. So we take these beautiful images and we process them into more beautiful inferred parameters. That's my job. That's what I do all day. Things like the mass in stars, the formation history, the properties of the gas, the nebulae in these systems, the dust content, their chemical abundances, the properties, abundance, size of any of the black holes. Okay? So that's what I think about all the time. And these are the things that haunt my dreams. And so we actually stand at a very awesome time to be studying this stuff. Right? There have been decades and decades of investments in studying the sky, and there are a few deep fields that have just been studied to death. And so we have these modern galaxy evolution surveys. They're multi-wavelength. They span the far ultraviolet all the way into the far infrared. This is just a picture of what that kind of looks like. The far ultraviolet over here, all the way into the far infrared over here, also including the radio and the X-ray. And you don't need to read all the words on this slide. Just know that there has been a ton of investment in taking very deep pictures of the sky with very wonderful telescopes that span the electromagnetic spectrum. Many students' careers, many engineering careers, many scientists' careers have been devoted to gathering all of this data. And so now it's on us to make some use of it. Okay. So I'll start discussing some of the modeling challenges. One of the biggest ones is here. This is Andromeda, gorgeous. Hey, the center, the little ball here at the middle, that's about the size of the full moon on the sky. And if you were to look up and you could see Andromeda with your eyes, it would span a large swath of the sky, several degrees. Okay. And then over here on the other side, this is more like the stuff I study. It's a distant galaxy. And you see the contrast here, and this is just a distant galaxy image at different wavelengths. You see the contrast here is that we just can't tell very much about distant galaxies. This is one of the fundamental challenges. We don't know what's going on. So I just talked to you about all the stuff we want to learn. And now I'm going to show you how weakly constraining our data are and the uncomfortable marriage between those two facts sort of drives much of my research. And so light from everything in this very complicated cosmic ecosystem, stars, nebula, black hole, etc., it's just combined linearly. We just add it all together. And so that leads to this phenomenon we call outshining. Most of the light comes from a few very, very bright things, gigantic stars. Either they're young or they're old, they get very luminous at those points in their life. Or maybe feeding black holes that can outshine the entire galaxy, or a supernova going off. It's just outshine the whole thing. Those things are great, but it's usually not what we want to know. We want to learn more about the dim stuff. And stuff we can't see very well, older low mass stars, dust, and planets sometimes. And so you have to infer the properties of the dim things by studying the bright things. This is just one of the basic building blocks of why this is difficult. And so this means our inference is often dominated by a lot of these modeling choices. What do bright things tell us about the rest of the system? something we think about often. I just showed some images. I will spend a lot of my time here thinking about something much more constraining, which is spectroscopy. And so this is just a spectrum of a distant galaxy as an example. This is from the Webb Space Telescope, so it's relatively hot off the press. But spectroscopy is richly informative. You have all these different patterns of emission and absorption features. And if your models are good enough, you can learn a lot from this stuff. In theory, in a perfect world in a lab where you make a fake galaxy and then fit that fake galaxy, you can constrain their formation histories and most of their physical conditions with a good spectrum to within a factor of 2 or 3, or often even better. So if the galaxies in our laboratory look like the ones in the universe, we can learn a ton from these things. Okay? Spoiler alert, they don't. That's one of our big problems. So this is why Bayesian thinking is just very powerful for thinking about galaxies. And we have sort of tens or hundreds of parameters, physical things we want to learn. And then we have these weakly constraining data. This means that the prior and data, they both matter. Right? The likelihood contributes a lot and the prior contributes a lot, and there's really no way around it. And this is kind of the sweet spot for Bayesian statistics. You can imagine a likelihood-dominated problem where it doesn't really matter what your prior is, so why bother writing it down? You can imagine a prior-dominated problem, and that, well, that's theory, right? That's not something we're trying to infer. But galaxies here, they sort of lie in this sweet spot where both really matter. And so it's really good to think about both and see what we can learn. So this is time well spent thinking about your models, thinking about your priors, being careful about your inference. Another key problem for galaxy formation is that we have this very complex emergent behavior, and that means the key physics governing galaxy formation are uncertain. The scales of galaxy formation are 20 plus orders of magnitude in both time and space. There's a leading simulator at Harvard who once said actually simulating galaxy formation from first principles takes something with the computing power of the sun. And that's about right, maybe an underestimate. And so what that means is you get these big simulations of the universe where people put galaxies in, but they kind of have to approximate the small scale behavior. They make up little rules that sort of make sense and sort of produce some of the things that we expect to see. But because you're approximating all of this physics, in this case, 8 different large scale simulations give 8 very different answers for the formation histories of these different galaxies. These are just 5 or 6 different types of galaxies and how they look very different in these cosmological simulations. And just so it's clear, the y-axis is 5 or 6 orders of magnitude. Right? So these small differences in wiggles are huge factors of 5, 10, 20, 100 difference in the actual formation histories of these things. And some of them are very, very different. And fire actually is probably the most accurate of these. Notice how different it is from the others. But it doesn't really matter. I'm not here to call balls and strikes here. The point is, do real galaxies behave like one of these? None of these? There's just not enough agreement from simulations. They don't predict enough of these microphysics or macrophysics even to use as a basis for fitting distant objects. So we take a fundamentally different approach. And we combine models of stars, gas, dust, black holes, and we write down little physically motivated priors, which are effectively educated guesses to try and do inference. And we try not to use any of these simulations because they're so different. If you take one, you'll probably get answers that look a lot like that one and rule out the others. Have you learned anything? Maybe not. So that's kind of the game here. And so that means Bayesian thinking, again, is very powerful for interpreting galaxy data. This is just a little movie of a fit. Here I'm adding different images to the data, and then we're constraining all these things we want to know. Normally, I show this movie to convince people that, you know, with high dimensional inference, MCMC sampling, and Bayesian inference here, you can put in one data point and infer something about 20 parameters, and it's not illegal. You actually get a pretty good answer, but I don't think I need to convince this crowd of that. This is fine. This just means our inference is working, and if you add a lot of data, you can learn a lot of things you want to know. but you'll notice not everything. And some of our posteriors are still very, very broad, even when we have a lot of data. So the universe can be arbitrarily complex, but as long as we can simulate the correct physics, we can marginalize over them, or in some cases, when we're lucky, measure them. Can we do that? Well, right now, the answer is definitely no. I'm going to try and convince you of this very briefly. And I think the big problem here for us is model misspecification. And there was some discussion of this yesterday. Galaxies have no ground truths. This isn't like the weather. You can't predict the weather and then go outside and look at it the next day and say, oh gosh, we were wrong. We don't have anything like that. Basically, we just have our models and our guesses, and the simulations aren't really there yet either. And so this is just an example. We have popular different modeling codes, which are applied to identical, high-quality, space-based images of galaxies. Everything's the same. Right? These are, 13 different analysis codes. And here, this is just showing the outputs for some 500 galaxies. And so just a couple things. The y-axis is how quickly they're forming stars right now. The x-axis is how massive or how many stars exist in the system currently. So this is fundamental to galaxy formation. This is like the most basic and important thing. How big are the galaxies? How quickly are they growing? And so the y-axis spans like 6 orders of magnitude, 5, 6. The line here, this black line, is the same in every plot. It's not a fit. And all I want to point out here is that these 13 different codes run by 13 very intelligent people who made very reasonable choices give very, very different answers. Okay. And if you are a galaxy formation aficionado, you'll stare at this and say, oh my God, some galaxies are dead. Sometimes they're not dead. Sometimes they're forming systems rapidly. Sometimes you have a ton of galaxies that are bursting with star formation. But all the answers are pretty different qualitatively. And you get very different pictures for how things like the Milky Way might have evolved. So why is this going on? And how can we fix it? This is pretty much state of the art, by the way. This is 2023, very recently. This was a huge feat of diplomacy, getting these 13 different groups in the room and agreeing to this test. What can we do better? Well, here we're just fitting imaging. And another key problem, in addition to outshining and not really knowing the rules, not knowing the models, we have this problem, degeneracy. The things we want to know often just look very degenerate in our fits. We fit an image, it could be anything. It could be red because it's very dusty, it could be red because it's very old, it could be red because it has a lot of heavy elements. This is just a fundamental problem to the field. And so with imaging, we're kind of limited to mapping out these degeneracies very carefully. And there's not a lot more we can do unless we have very informative priors, which is one of the things we really need. Fine. Imaging isn't enough, but I already told you about spectra. Spectra are very, very informative in principle. You have all these lovely patterns of emission and absorption features that you can learn a lot of physics from. And so here, this is just another experiment. Some of the best distance galaxy spectra we have. This is something like 3,500 galaxies existing somewhere between 6 to 8 billion years ago. Each has a 20-hour spectrum. So you point the telescope at one object for 20 hours. It's a Herculean effort. This took many years. From a gigantic telescope, an 8-meter telescope. That's the diameter of the mirror. So this thing is the size of a medium-sized building. This yields an incredibly high cellular noise for people like me, 20 to 50 per angstrom, and then angstrom's 1/10 of a nanometer. So these are just absolutely exquisite spectra. Do we get the same answers if we have very, very good data where the likelihood should dominate? Are we there yet? And so now we only have 3 leading inference codes, but we're doing the same thing again. And here, for these beautiful, beautiful spectra, I'm just showing some basic things. These are code 1 versus code 2 versus code 3. And this is the abundance of elements in stars, and pretty much a scatter plot. Not good. Not good at all. And to be clear, all of these codes fit the data very well. That's never the problem, sadly. We can always fit the data, but knowing what it means is the real challenge. And you can go on and think about ages or formation histories, and you see the same problem. Okay, so we can't figure it out from imaging. and spectra, where the information should be there in principle, we still have these. I mean, well, you could look at these yourselves and decide whether or not we've solved the problem. So why? What's going on? Why can't we crack this? We aren't dumb. We're using good models. We have excellent models of stars, gas, dust, everything. What's going on? The basic problem is we cannot cram enough physics into these models. Galaxies are too complicated. And there's many different types of physics in play, and that just sort of forces approximations. It creates modeling specification because you can't fit it all, or at least you weren't able to. Right, and so, of course, all models are wrong. Some are useful. Kyle beat me to that, but you have to say it every time, and it's really important to keep in mind when doing this work. And so I'm just going to show a little quick movie. On the left here is a physical parameter I want to know from a galaxy, and on the right is the approximate size of its effect on the data. So let's go ahead. What are we dealing with? And that list goes on and on and on. I stopped it here because we only have so much time. But this is the core of the problem. We need to cram all this physics into our models, and we only have a finite amount of time. Modeling capacity. So, inference, powerful but sometimes dangerous. All models are wrong, but some are useful. Kyle beat me to it, as I mentioned. But you have to keep it in mind. It's so important to say. What does useful mean? We create new knowledge. But we really have to understand our data, measurement uncertainties, instrumental effects. You must have reasonably accurate generative models for what we're fitting, and that's the part we have, but we can't quite harness yet. And if this isn't true, careful. You can get the wrong answer, and you can be confident about the wrong answer. So how do we bridge this gap? Well, I do want to say it is definitely clear that adding more physics can solve super big problems. This is what I spent a lot of my time thinking about. I'll just show you one example of this. The details don't really matter, but this is the growth rates of typical galaxies. And the solid lines is what you expect from simulations, and the dashed lines are what we see in the data. We had this problem where we were offset by a factor of 2 or 3. This problem persisted for many, many, many years. And this is when we're fitting small, low-dimensional models, 4 or 5 parameters to the data. And so I spent a lot of my postdoc trying to push this forward. We got up to something like 15 parameter models. And that solved this problem. We suddenly had excellent agreement with simulations. And now this cosmic star formation, right? The growth of galaxies across time looks a lot like more what we expect from the simulations. And that's something the simulations agree on. And so we can solve big problems by adding more physics. But this was extremely expensive. We didn't do it efficiently at all. And there's a lot more puzzles we want to solve. So how do we kind of bridge this gap? Well, the problem is, of course, high-dimensional models, we're already pushing computational limits. Very high-dimensional models just don't live on a grid. It's not possible. You can't store them all to disk. You have the curse of dimensionality. You need a Google data center or something. So that means each model, you kind of have to generate it on the fly. You have to add up all these gigabytes of stellar models, gas models, dust models, black hole models, and that's just a compute-intensive task. It takes something like 15 hours to fit a normal galaxy. And so that means you need several million CPU hours to analyze a typical deep field of the sky. Why is this so hard? What drives the requirements? Well, start with galaxy observations. You can generate models very quickly. This is just adding up all the stuff that we know exists in there. You don't need to read the words. But the point is, we spent a lot of our time making this ultra fast. You can generate maybe 20 models a second. And then you run something like MC or nested sampling, and you need maybe 1 million models per fit to get a good sense of the posterior. Well, you just multiply these two numbers together, you get 15 hours per object. And so one of these things, or both of these things, needs to go faster. One thing you can do is build a neural net emulator. And we've been doing this a lot recently in the last 5 years or so. Basically you replace all the physics and just say, we have some inputs, we want some outputs, replace all the physics with this big neural network. And then this speeds up our model generation time already by factors of 100 to 1,000, or if you're lucky enough to have a nice GPU, you can get up to 10,000. And so this has a lot of attractive properties. I already mentioned they're fast, There's some trade-off time between the width of the neural network and how quickly it runs. This dashed line is all of our normal models. So as long as we're below this dashed line, we're still winning. But we need to trade off precision to move up and down this line, right? And so how much precision can you trade off and still get the right answers? This is just a test. This is uncertainty in this funny unit of magnitudes. Don't worry about it. As a function of wavelength, again, don't worry about it. But the point is you have different size neural networks. They give you different levels of precision. And so we figured out after running a ton of test fits, as long as your neural networks are adding less than about half the observational uncertainties, you're going to get about the right answer. And that's what we find here. This is just the slow way using all of the physics, the fast way with the neural net emulator. And we're able to get answers within the observational uncertainties much, much, much quicker with these approaches. And so this is really great. Of course, as you all likely know, you get other things from replacing your models with neural networks. You get back propagation. And so this opens the door for using things like gradient-based samplers. And differentiability just allows very efficient sampling. If you use a classic random walk sampler, you're kind of stumbling around looking for the solution. But if you use a gradient-based sampler, you can get there very, very efficiently. There are other challenges, though, with this approach, multimodality, but it's fine. They're much more efficient at this, and we can use them with neural networks. So this is stuff we already have in place over the last couple of years. It can do a lot of cool things. It can't quite do as much as we want. But this is just one example of what it can do. You can't maybe see all this, but if the lights were a little darker, you would see a lot of galaxies in these deep fields. This is from the James Webb Space Telescope. And so you can use these neural net emulators to sort through thousands, tens of thousands, hundreds of thousands of sources and look for things that are really, really exciting. In this case, one of the most distant galaxies ever seen. And Bingji Wang has spent a lot of time doing this and found the second most distant galaxy ever using one of these techniques. So it's very exciting. You can do real important science. So we can do this stuff faster, but I promise you we can do something new. And I want to talk a little bit about the new things we can do as well. And so this decade, this is kind of a really exciting time to be thinking about this. There are these multiple large-scale spectroscopic campaigns to map out these large fractions of the observable universe for the first time. And we're just going to go through one of those maps right now. You get a spectrum, you can get a distance, and you can build this amazing map of tens of millions of galaxies. And so I'll show you some of these investments in a bit. This is from the DESI survey. But people are building these things because we don't know what dark energy and dark matter are, specifically dark energy. And having these maps is just so very, very helpful for actually putting constraints on dark matter and dark energy. And so they also happen to be great for galaxy formation. And so we are living in the decade when all of this is being mapped out. Right now, DESI's actually almost done. So here, this is DESI. It's going to get spectra of something like 50 million galaxies. Euclid, which just launched, is going to get something like 35 million galaxy spectra. We have another one, PFS. You can't see this at all. That's fine. This is, it goes redder, deeper, but it's a bit more expensive. We get something like 5 million galaxy spectra. And then the Roman Space Telescope, if it launches, cross your fingers, and we'll get something more than 100 million galaxy spectra. And this is insane. I did my thesis about 10 years ago, and I spent several nights on a telescope getting 7 spectra, which formed the basis of my thesis. There's been a massive change in the technology used to do this, specifically multiplexing. You can take many spectra at once. That let us just totally change the game here. We can get so much more data. So, can we analyze spectra better? Okay, can we think about this? Talked about a neural net emulator for images. What about the spectra? There's much richer information in there, as promised. This is the most distant dead galaxy in the universe. We found this with our team. It existed when the universe was about 800 million years old, and it's already done. It's done forming stars. It turned off. Okay, that's something like 8 or 9% of the age of the universe. Most other galaxies take much longer. So it's a real puzzle. So if we can analyze its spectrum, we can learn maybe why that happened. But these are harder to do. Instead of trying to predict 10 images, you're trying to predict thousands of pixels. The input physics are much more detailed. You need to worry about complex things like gas physics. So you go from 10 parameters you're trying to learn to maybe 30, 40, or honestly, I'd love to crank that number up to hundreds per galaxy. Okay. And you also need many more nuisance parameters, controlling things like the flux calibration, the broadening through the instruments, through the motions of the stars, modeling of outlier pixels. You worry about emission from the sky all the time. That's a complicated headache that you need to deal with on a case-by-case basis. There's a lot of correlated noise, which frankly, no one's really opened that door yet at all. So there are a lot of nuisance parameters you worry about when fitting these very information-rich pieces of data. And so classic nested sampling fits. I told you imaging takes maybe 15 hours. And now we're talking about a couple of days, up to 5 days to analyze one spectrum. And I'll remind you, we have hundreds of millions of spectra now. So we're kind of working very quickly to try and make this a more feasible problem. And the first thing to do is to wrap neural nets around the slowest parts of these physics. These are the pillars of creation. You've probably seen them, the Eagle Nebula. And so this is a star-forming region in a galaxy. It's a huge ball of hot gas. This gas is ionized or photoionized by bright young stars. And you can see some of them here. These little regions are sort of fractally complicated. You have complex physics. You have this crazy geometry in this case. It looks like, kind of like the fingers of God or something. You get hundreds of parameters easily trying to describe them nicely. But they're important to model because they're the best way to count young stars. You can kind of see the recombination emission lines that tell us how many young stars there are. That's very important. So we want to understand them really well. One of them is already hard. Galaxies have, of course, hundreds or thousands of them typically. So this is just a bunch of small H2 regions circled, and then a lot of even smaller ones are not circled. And so normally you have to run these things called photoionization models. They take maybe 2 minutes to produce one model for one of these complicated regions. And so here, one of my grad students just wrapped a neural net emulator around it. She was able to speed this up by factors of about 10,000 using the neural net emulator. And we're able to predict all of these rich information or information-rich emission lines. We can also kind of do new things. And so this is exciting for people who study galaxies, but we can imagine instead of stars in an H2 region, you can imagine it being powered by a black hole or by fast gas shocks or other things. And so we're able to make this work much more source agnostic and allow for surprises or discoveries by studying these. And so this is just an example. Here we're trying to measure or infer what the average ionizing spectrum looks like, the far UV radiation, by studying optical and near infrared emission lines. You can never see the far UV really in galaxies. It's invisible for physical reasons. You can measure the emission lines really well. And with these very rapid inference codes, now we can kind of reconstruct what the ionizing radiation should look like. And so this is one of the ways we're just trying to speed everything up and bring it all together, bring it all in one giant inference package, hopefully. And so this was a huge leap. This came out in the last year or so. We'll wrap it in a larger inference package soon. But I just want to show you one example of why this is cool. This was used in the discovery and characterization of the current record holder for the most distant galaxy. This came out just a few months ago. Here it is over here. It's called MOM Z14. MOM is not what it sounds like. It's Mirage Variable, the name of the program. Okay, there's some others here. But this existed when the universe was about 290 million years old. This is just super cool. I mean, 290 million years old, that's not very much time. Sharks have been around for longer than that. So we're really close to the Big Bang here. And Q reveals there's something in this galaxy pumping out hot photons faster than normal stars. Not normal at all. Very weird, something special about the first generation of stars. There's way too much nitrogen in this system, which you're like, okay, what does that mean? That means there's some exotic element production going on that we really don't understand, and this was very exciting to see. There's also very surprisingly dense gas, characteristic of the early universe, but even denser than we expected. And we wouldn't have been able to infer any of this as efficiently or as quickly as we did without having things that's sped up by a factor of 10,000 and can do many more combinations of physics as we learn more things. So this is great. This is already working nicely. Ultimately, we want to fit everything at once. We don't want to pull out the emission lines and learn about the ionizing spectrum on its own. We want to fit the stars, gas, dust, black holes, everything at the same time. This is something Emily is working on. So we're just combining all these neural nets into one giant system. It replaces all the gigabytes of normal models we use. And so I already told you a little bit about the nebular stuff. There's also a stellar component, and we can play the same game where we emulate these large databases of stellar spectra and stellar evolutionary tracks. And this, for several reasons, this actually works extremely well. And we can get typical errors of less than 1% on doing this process. So we can cram all sorts of new physics or more parameterization in here because everything's faster. Additionally, it is just like emulating imaging. It's also a lot faster to emulate spectra. So this is an unfair comparison. The red line is what we've built in my postdoc. It's on a CPU. The blue line is on a GPU, an A100. But it scales very, very nicely. Number of spectra come out very quickly compared to runtime. And we also get these additional speed ups from gradient-based sampling, although there's a challenge when running something like Hamiltonian Monte Carlo. The likelihood space is highly multimodal, and so we're trying to think about how to cleverly initialize or maybe reparameterize or maybe use SBI for smart starting positions. I told you we have problems. There's more to come. But this is one of the ones we're thinking about. We have a very powerful new tool, so we're thinking about how to use it. And we can do this to fit these beautiful surveys of the universe, and we will, but we can also do new things. And I just want to show you one of the new things we can do. So there's this problem in the early universe where star formation is very bursty. That means galaxies will flicker on and off. They're like candles or light bulbs, where you have an explosion of star formation. They get super, super bright. Then they blow out all their gas. They stop the star formation. They get really dim again. So you have this oscillating feature up and down, and they'll kind of flicker in and out of our surveys. And that means when they turn on, they kind of blow out all their history information. You can't see any of the dim stars that contain all their history. And so this is a pathological problem. Here is still the noise of 100 spectrum from the Webb Space Telescope. It's generated by Bing Wang. This is a model spectrum. Right? So it's perfect, right? There's no epistemic uncertainties. There's no model for specification. This is a perfect world, a perfect lab, a perfect spectrum, and a perfect fit. Right? Here, this dotted line was our input formation history. And this purple line is our recovered formation history if we assume there are no bursts. And this galaxy is just smoothly forming stars. And so we recover, on average, the right solution, but we completely miss the up and down behavior. It's just obliterated. Right. Fine. Well, that's a perfect fit. What if we give it a prior that says this thing should be bursting, this should be going up and down? Doesn't really work. Still doesn't work. So we fit one single burst of the most recent stars, and we just blow out all the rest. There's nothing more to learn. Okay. And so this is a simple version of a bursty prior. It just allows for large changes in the star formation rate. And we still can't get the right answer here. Okay. And so in addition to missing these up and down fluctuations, this burstiness significantly degrades the accuracy in other ways. You can't get the mass out. You can't get the average star formation rate out. You can't get the age out. And this is true here, even if we know it's bursty, even if we generated this perfectly in a lab. So you can't learn it by fitting individual objects. But with all these fancy tools that can generate model spectra very quickly, we can do something totally different. And this is extremely effective. Instead of modeling one object, hopelessly degenerate, you can model entire populations of objects all at the same time. And so if you imagine sort of a room full of light bulbs and they're all turning on and off slowly, maybe at different frequencies with different powers, you take a snapshot of that room, you have no idea what's going on. And for one light bulb, but if you have the whole thing, you have this little model, galaxies going up and down, you can get much, much more information. And so modeling galaxies simultaneously as populations is a hugely effective approach. This is opening the door to all sorts of cool stuff. It was literally impossible 7 years ago. And now we can do it kind of fairly easily. So there are many teams doing something like this, including try to marginalize over the entire galaxy population and learn about cosmology, and this is also very effective. I won't talk about this at all. Okay. But modeling multiple galaxies at the same time as a population, we can do different things. So it's impossible to measure for one object. It's a long-standing problem, but we can fit them all at once. And so here, this is just Emily Burnham's work. I'm going to walk through a little bit of how this works. You can imagine generating populations of galaxies that flicker with different powers on different timescales, and they produce different distributions of observables. Distributions, any one galaxy is hopelessly degenerate, but the distribution is quite actually well constrained. And so you need kind of a complicated model for this. Here we just have a power spectrum of changes over different time scales. Okay? And so you can then constrain the power spectrum of possible fluctuations in galaxies. You assume it's stationary, and things upbursts, there's likely downbursts, which isn't quite true, but it works well enough. And so if you assume different lines in the space, different power spectra, you get very different formation histories. And you also get different distributions of observables. And now we can ask qualitatively new questions. And very, very, very importantly, I showed you earlier on all these different simulations with different behaviors in the space, different formation histories. We can actually constrain them directly with this. And so we could say, this is wrong, this is wrong, this is wrong, this is maybe right, this is on the right track. And it's just so valuable. We can finally start falsifying these things. Fitting one galaxy is very hard. How do we do populations? This is why I'm here. This is why I'm excited about simulation-based inference. And if we tried to do this with our old methods, it would take something like 20,000 core hours per population fit. And you always do it wrong, so you want to do that many times. It just doesn't work. So instead, we can train a simulation-based inference algorithm. And this lets us do all sorts of cool things. I'm not going to explain SBI. All of you know how this works. But we can marginalize over all of our nuisance parameters. We can include measurements and Poisson counting noises for small surveys. We can train on a cluster. It runs in seconds on a laptop. We can put all this physics in. We can get out really good answers, actually. And we just have to be smart about it. And that's the hard part, I think. This is just an example of what we can do. And we have all these data. Now we can finally do good science with it with these techniques. So this is here, the red line is one simulation. The orange line is another in this power spectrum density space. And we simulated galaxies from the red line, and then we fit them with this SBI pipeline. And we're just kind of assuming a modest size survey with the James Webb Space Telescope. And we get out very good answers for the most recent star formation rates. And we don't see the older ones because there's so much burstiness. That's fine. Our uncertainties are well calibrated. We're happy with that. And we can measure these different fluctuations very, very well, finally. We can go back and falsify all these little rules we put in to make the galaxies turn out correct. And so this is solving an ancient problem in my field with these high-dimensional, fast inference pipelines like SBI. I am super, super excited about this. This was literally just a thing we throw our hands up and say, well, we'll never learn that. And now it's actually tractable with these kind of approaches. So I'm really stoked about this. This works just amazingly well, and Emily's done a great job here. So we want to tackle some even bigger problems next up, things like epistemic or model misspecification uncertainties, and also just kind of let this rip on all the deep web data. I mean, it goes so fast. Why not? It doesn't take years like other investigations do now. Hey, fine. This burstiness population model, well, I promised I would do something with spectra. I sort of cheated you a little bit. I'm only taking a few very well chosen, very informative features from those spectra. What you really want to do is actually something more complicated. You want to fit all the pixels. They have so much more information. But that's a hard problem, as I'm sure you all know. There's lots more to learn. There's lots more pixels to use. There are far more data coming. I'm talking about fitting hundreds of galaxies. But I just told you, we're going to have hundreds of millions of spectra from these large-scale surveys. So can we adopt SBI to fit the entire spectrum? Hey, this is what I'm thinking about with Josh Ingram here, and Lee, Josh Spiegel. This is something I'm very excited about, and we're starting to work on. There's just some of the key challenges, stuff we're thinking about. I told you, our physical priors are fuzzy. They're good guesses. They're heuristics. We really need to update them. We probably want to update them while running this. Okay, can we do that with SBI? Probably, in some ways. We have to adapt it a little bit. we are rife with model misspecification. Astrophysics is hard. So can we solve that on the fly or afterwards? Can we do this all at once? We kind of have to. No one's really done it yet. Can we balance coverage in this space, in these highly dimensional spaces, and have highly informative priors? Kind of separate our coverage and our priors in our training sets. Something we could think about. And Anne and her group have done a lot of great work on different techniques for this. And another thing, selection effects are very strong. You only see the bright things. You want to model the whole population. But you also want to model your selection effects as you're doing this. And your selection effects or your understanding of them will change as you're running the fit. So all of this, in principle, is a complicated thing to do. But I think we finally have the tools to start asking the right questions and doing this. And so this is kind of an awesome time to be in this field, I think, where you can actually tackle these. So second to last slide here. I just want to say there's been this big computational and inference and statistical revolution. So time to fit galaxy imaging using on-the-fly model generation. When I started my postdoc in 2017, it took something like 104 hours per object. Spent many months in the code mines, cranking out 5-10% efficiencies, replacing for loops and so on. We got this down to about 24 hours. This is on Fortran code, by the way. And then all of that kind of didn't matter so much. A couple of years later, we replaced the whole machinery with neural net emulators. We're down to 10 core minutes per object. Add in things like GPU acceleration, differentiability. We can get down to something more like 1 core minute or 1 GPU minute, maybe. And now we have something like simulation-based inference, 10 core seconds per object. And you can do that actually on a CPU. This is insane. This is a factor of something like 10,000 speed up in 5, 6, 7 years. And so that's kind of a transformational number. Now we can actually efficiently model these complex systems with hundreds, thousands, tens of thousands of parameters in some cases. We just need to be able to write down the physics, put it in the inference code, and think carefully about our nuisance parameters and our modeling effects. So we have the capacity, and that's why I'm here. I'm really excited about this, and now we just have to do it. So I'll just leave up my slides here. New things, future things. Thanks, everyone.